Hey, good afternoon, everyone. This is our last class, as you know, and the plan for today is I will spend the first 5 or 10 minutes wrapping up discussion of microcavities because we didn't have a chance to finish discussion of nanobeam cavities last time. And after that, Raul will talk about numerical methods in electromagnetics and their applications to cavity design. And I'll stay online, of course, in case you have any questions for me as well. So let me just very briefly wrap up what we did over the past couple of classes. We talked about cavities that confine light by combination of the distributed Bragg reflection and total internal reflection. And we looked into cavities on the right that confine light by distributed Bragg reflection in 2 dimensions and, distributed Bragg reflection in 1 dimension and total internal reflection in 2 dimensions. So these are DBR microposts and also 2-dimensional planar photonic crystal cavities that have distributed Bragg reflection in 2 dimensions and TIR in 1 dimension. So if you compare them, there are some advantages and disadvantages of both of this, right? So for 2-dimensional photonic crystals, in order to open a photonic band gap in all the different directions in plane, you generally need high refractive index contrast, right? And on the other hand, with 1-dimensional DBRs, you can actually make a DBR even with low refractive index contrast. In fact, some of the DBRs that we studied, even in the homework, have very low refractive index contrast, 3.6 versus 2.9. And you wouldn't really be able to open a 2-dimensional photonic band gap with something like that. So that's the good thing. You can, in principle, make 1-dimensional resonator, even with low refractive index contrast. But then there are problems with these DBR micropillars because they're made by growing the layers of different materials on top of each other. Even today, after many decades of working on these particular type of resonators, there are still issues in finding materials that are lattice matched to each other so that you can grow mirrors. And in particular for vertical cavity surface emitting lasers, where, for example, for 1.5 micron lasers, which are based on phosphide materials, people are still struggling to find the right types of materials that you can use for mirrors. So what they typically do is they make quantum wells based on phosphides, and then they wafer bond gallium arsenide and aluminum arsenide as mirrors because they're not absorbing there, but they can't really be grown directly on the phosphide materials. And if you just try to grow directly, there would be lattice mismatch and defects, and that would actually, of course, cause additional absorption and roughness and Q degradation. So there are unsolved problems there. And we also, of course, talked about other issues that if you would like to, have a high Q factor, small mode volume, you have to etch very high aspect ratio structures. Masking it is pretty hard. And finally, for some applications, such as Face ID on iPhones, you want to have surface emitting laser, but that's not the case in all applications. In a lot of photonic integrated applications, you would like to have a laser that you can easily integrate with the rest of the photonic circuit. So having a surface emitting laser is not really optimal scenario for that. It's much easier to have something that directly couples to waveguide. So now the question is, okay, you have here something where you can more or less just by simple shallow etch make a resonator. That's on the left, and then on the right you have a system where you don't need a very high refractive index contrast, but then there are other issues with fabrication and growth and so on, which is motivation behind these nanobeam cavities that we will talk about today briefly. And nanobeam cavities are essentially just planar DBR cavities. It's the same as the DBR micropillar cavities that we talked about before, except that in DBR micropillar cavities, you are growing mirrors by stacking layers of different refractive index. And then in the planar 1-dimensional nanobeam cavities, you're basically making mirrors by etching periodic structures inside of the material with high refractive index or higher refractive index than the surrounding. So this is the same approach as what you have in 2-dimensional photonic crystal, except that you apply it in 1 dimension. And since it's done in 1 dimension, you don't really need a very high refractive index contrast to build a resonator because you're using distributed Bragg reflection only in 1 dimension and total internal reflection in 2 dimensions. So if you go back to band diagram, right, you're basically just talking about 1 direction of band diagram, as if you're only interested in gamma X direction. And there, even for low refractive index contrast, you'll always open a band gap at the end, actually, of this brilliant zone. You don't really need band gaps to overlap in all the different directions. So this particular cavity that we see here, although it's hard to see that it's a cavity, but it is a cavity because there is a modulation of the periodicity here as you go along the axis. is in fact made in silicon dioxide. So it's a very low refractive index contrast, right? You have glass, basically 1.5 versus 1 air surrounding region, but that's still enough to localize modes, as you see from electromagnetic field profiles at the bottom. And the reason, the motivation for making cavities in glass here was because silicon dioxide is very good material for biosensing applications, and it also, you can actually use it to make cavities in the visible wavelength range because it's not really absorbing at the visible wavelengths. So how would you make something like this? I mean, this is illustrated for silicon dioxide cavities, but you know, of course, the fabrication is pretty much the same as fabrication for two-dimensional photonic crystals. I mean, you just start from some planar stack, whatever material you would like to turn into a cavity, sitting on some sacrificial layer that you would undercut, and then you may have a substrate or not. Then you do E-beam lithography, dry and wet etching, and that's it. And then you end up with these suspended structures that are cavities. For silicon dioxide, I mean, in this case, it's a little bit different. You don't really need a 3-layer stack. You just oxidize the top layer of silicon. You etch with masking after electron beam lithography, dry etching, and so on. And then you can do undercutting by using xenon difluoride undercut to undercut silicon underneath. And that's the same as the step that we saw when we talked about microtoroid cavities, which people use to undercut the region under the silica. So fabrication is exactly the same as for planar photonic crystals, so we're not going to go into details. Again, here I'm actually highlighting this. Of course, you can make it in a high index materials, but this is interesting because silicon dioxide, again, would be too low index to make two-dimensional photonic crystal. But if you can make pretty high Q one-dimensional photonic crystal cavity, and that's the same one as I showed you before, where you're basically just modulating period following this parabolic relation. You don't even see how it's changing, but you're changing it, and you're localizing field at the center. And Q factors here are pretty good. I mean, they're even higher than 5,000 with mode volumes around 2 cubic optical valence when refractive index is just 1.5. So that's nice, and it's in the visible wavelength range. So that was the motivation there. Of course, you can make it in a variety of other materials. You have one dimension in which you are introducing these distributed Bragg reflectors. So often you will see people make these types of DBRs where you're just etching these kind of rectangular shapes. And this was adopted from the paper that I'll show you later from Caltech, Oscar Painter's group. But you can also introduce a resonator by making circular holes along the axis. And this is in gallium arsenide with in-gas quantum dots, active material, and even lasing was observed from these particular systems. And actually, you can also do electrical injection, as what we've seen in the case of two-dimensional photonic crystal laser. You can actually introduce lateral PN junction and inject light into this cavity region and make the cavity actually emit light from the cavity mode that is illustrated here. So again, the design, and after I finish this, Raul will be talking more about that, will be done using a variety of numerical techniques. I mean, you can actually kind of make some order of magnitude estimate on the design before you start using numerical methods on kind of what kind of periodicity you would need and what kind of cross-section of the beam you would have, but then ultimately for designing exact shape of this defect that localizes light and finding what cavity field you have inside, you will have to use numerical methods that we'll be discussing shortly. And a lot of work on these nanobeam cavities has been done in the context of optomechanics. This is from the work of Oscar Painter at Caltech, and a lot of work on this has been done also by Amir here, Safavi Naini, who was Oscar's student. So he also did a lot of work back then when he was at Caltech. And the idea there is that you can actually make cavities, these cavities that support high Q modes, as what we've seen from the previous discussions, high Q optical modes, but they can also simultaneously support high Q mechanical modes. And of course, two-dimensional photonic crystal cavities can also support mechanical resonances, but they're bigger and heavier, so their mechanical resonances would be at lower frequency. And with these nanobeam cavities, since they're basically much lighter and smaller, they have smaller mass, their mechanical resonances would be at a higher frequency. So there'd be a lot of work on, I mean, that's not just fundamental interest, it's also practical interest because people are thinking about using a lot of these systems for frequency conversion, quantum frequency conversion, matching, for example, superconducting qubits to optical qubits and so on, or for sensors. But the reason why people started thinking about one-dimensional resonators is, again, because you can produce higher frequency, higher mechanical resonance frequency, mechanical modes, which also have high Q factors. And that's actually happening at the same time as localization of high Q optical resonances that we already discussed. So for this particular resonator here, which was in silicon, you have multiple optical modes that are shown here on the right, and also you have multiple mechanical modes. And this is this profile here is showing you how kind of cavity stretches as it oscillates mechanically. And also I'd like to point out, since we're talking about optical resonators here primarily, that on the left you see optical band structure for this system, and this is different from two-dimensional photonic crystal resonators because it's only a one-dimensional system, right? So this is plotted for this one-dimensional periodic structure, and also you see where you would localize the modes if you're introducing this change in the periodicity. And the same thing, but for mechanical modes, is done at the bottom. So this whole field of optomechanics, in the field of optomechanics, actually the idea is that you build the systems that support optical and mechanical resonances at the same time, and then by exciting optical resonances, which also produce radiation pressure inside of the system, you can produce mechanical vibration on the system, right? So you can also excite mechanical resonances. And then you can see signatures of mechanical resonances in the RF spectrum of the system, just by looking at the RF spectrum of the system, right? So at the bottom here, for this particular resonator that has optical and mechanical resonances, you can see optical spectrum, right? And this optical spectrum, you have different, first, fundamental, second, and third order modes with different Q factors. Those are the modes that are shown on the top left. These are all optical resonances. They have, pretty high Q factors. And in this experiment, they're just exciting certain optical mode. I believe it was fundamental by radiation pressure that would also excite mechanical resonances because optical and mechanical modes are coupled in this system. And then you would see in the RF spectrum of the system, these different mechanical modes. And shapes are again shown in the picture on the top right, and the RF spectrum is shown at the bottom. And you see that their mechanical resonances are in the range of around gigahertz. So if you look at the two-dimensional photonic crystal resonator, like the ones we discussed last time, you can also observe mechanical resonances in that system, but they would be at much lower frequencies, right? They would be, megahertz range or maybe tens of megahertz range, much lower than for this particular system as a result of much smaller mass and a footprint. So that's the idea here. And, of course, gigahertz is more interesting if you want to use it for any applications. It's a higher frequency, it's faster, and you can also use it for, as I mentioned, quantum frequency conversion between microwave range and optical range, right? Because you can use this optomechanical coupling to couple modes between two different parts of the spectrum. And there was recently some interesting work also from the same group at Caltech in that direction. So that's all that I wanted to tell you that was left from the last lecture. And now I will let Raul tell you about using numerical methods for designing cavities. But before he starts, because this was the part of the lecture that I was in charge of, I'd like to tell you that it's been a pleasure teaching you in this extraordinary quarter. And I really hope that you managed to learn something that you would use in your future work in EE340. And it's been also a pleasure connecting with you twice a week through Zoom. Although we didn't have a chance to talk in person, I know many of you from Stanford, and I hope that soon I will see you again in person, and I hope to chat with you in person in some better times. So, take care, and I'll stay online and I'll let Raul talk, and I'm happy to talk again with you. I just wanted to make sure that, I close right now, because if we have too much to tell you in the second part of the talk, I may not have time to say bye. So I don't want you to disconnect before I say bye. Okay, thank you, folks. So I now will let Raul share the screen.
Thanks, Yelena.
Thank you. Thank you all. Thank you, Lucia.
Thank you. Yeah.
Thank you. Thank you, Yushu. Thank you all.
Hey, hello. You guys can hear me?
I hear you.
Okay, great.
I think they probably hear you.
Yeah. Yeah, okay, so as Yelena said, I'll give you a very brief introduction of computational methods in nanophotonics. So I'll mostly actually, because we have 3/4 of a lecture left, I'll mostly focus on FDTD. And even in FDTD, I'm not going to give you the whole thing. This is not really meant to substitute a proper computational ENM class, but rather to just give you an idea of how what FDTD is, because it's one of the most commonly used numerical methods for modeling devices in nanophotonics. So what's the rough idea behind how you set it up, and what all can you do with it, which is probably more useful, because most of us don't really need to program, at least in this day and age, program our own FDTD. I think things were very different in Yelena's time, but most of us don't really need to program FDTD on our own. Yeah.
Be careful what you say there.
Well, you programmed FDTD. Right?
I'm joking. Yeah, I wrote FDTD.
Yeah. Yeah, now you can kind of pull off, pay a little bit of money and simulate devices. I'm joking. There's a lot of open source software.
It's actually true. It's true.
Yeah. So since most of you don't really need to program FDTD, it is less important for you to know exactly how it works, and more important for you to be aware of, what are the various approximations that go into the FDTD method that you would need to maybe play around with to get accurate simulations, and how can you simulate, different things with it. So if you want to calculate a band structure, for example, and this is a question a lot of you have asked in office hours, how do we produce the plots for the 2D band structures that you saw in your lecture notes and lectures. So how do we go ahead and do that? So we'll talk a little bit about that. All right. So it's a very, very rough and introductory overview. And if you have any questions, please feel free to ask. I'm not really an expert on this stuff, but I think I should be able to handle most questions. So let me start by giving you, a bigger picture view of different simulation techniques that exist in electromagnetics. So as you know, when we are doing nanophotonics, we're essentially just doing an EM simulation. And EM simulation has been done in many, many fields other than nanophotonics. In fact, for the longest time, the people simulating electromagnetic devices used to be microwave engineers. So people who would actually go and design RF circuits, and they were doing a lot of electromagnetic simulations, and people from spectroscopy community, remote sensing communities. So a lot of different communities have been doing electromagnetic simulations in a variety of different contexts. And then, of course, people in photonics community have more, which is, I think, one of the newer ones of all of these electromagnetic communities. They also use these techniques. So broadly, EM simulation techniques we can classify. If you take a look at all the simulation techniques that exist over all of these communities, you can classify them into two categories, or at least I like to classify it in this particular fashion. There are, of course, perhaps more intelligent classifications out there. So one technique I call general purpose methods. So they are methods that you can apply to any problem, right? So if you have any device or any structure, any permittivity distribution, you can throw a general purpose method at it. And there are many more general purpose methods than what I've written down here, but these are two simplest to program and easy to use. So finite difference time domain method, that's what we'll focus on. There's also finite difference frequency domain methods, which is just the frequency domain version of the finite difference time domain method with some caveats. There are also things like finite element method and so on, which can also be applied to almost arbitrary permittivity distribution, but there are some caveats here and there if you want to use them, right? So these are general purpose methods. So, and the good thing about these general purpose methods is that, they exist in the community, like it exists in different communities. People have already written programs that are fast, optimized, and you can essentially just find one of these programs online. There are a lot of open source programs that are available. For example, MIT has the MEEP FDTD package that you can use. It's an open source program. And then you also have, of course, more easier to use software that you might need to pay for. But typically, if you're going along the directions of using general purpose methods, then you would never really need to program it yourself. And that's very important with all of these computational methods. You shouldn't program anything yourself unless you absolutely need to. Use what other people have done and make your life easier. No, but of course they're slow. Then slower, but for most problems that we would like to handle, they're probably fine. But then they become slow if you are looking at maybe very large scale problems, right? So in remote sensing community, for example, they try to simulate entire forested areas. They're trying to understand how satellite radar signals scatter off entire patches of geographical land. And then they need to run pretty large simulations in order to do a model that big. And using something like finite difference time domain is really not feasible for them. So they can't really discretize an entire forested area and simulate it, right? So then they go for what I call problem specific methods. So they are methods that are tailor made to certain kinds of problems, so that you can't really throw an arbitrary permittivity distribution at it. But if you were to make some specific assumption on the class of structures or the class of problems that you want to simulate, then you can start using these problem specific methods. And here I've put down a list of methods that I know of. There's many, many, many more simulation methods that exist. So things like, Fourier modal methods, RCWA, for example, can work very fast for periodic structures. So if you know that your structure is periodic, you don't really need to discretize like 100 periods of the structure. You can do something smart and simulate with just one period, right? Or you have integral equation methods that work for permittivity distributions that can be described by a few interfaces. So if your permittivity distribution is not really complex, it's not very complex, but it's just like, maybe an interface with some arbitrary shape, you can simulate that pretty fast using integral equation methods. And antenna design community, which existed 30 years back, they use integral equation methods a lot, right? Because their antennas can just be described by a shape, by an interface. So it's a perfect electrical conductor. It's a very good model for antennas, and you can describe it by just the outer shape of the antenna. And then you can use an integral equation method to simulate pretty large centimeter size antennas pretty fast, right? So you have this problem, and then beam propagation methods that people use in simulating physical optics, where you want to simulate, actual, like how does a lens work, or how does a mirror work with free space optical devices. They're pretty large devices, but you can make some approximations there and use ray tracing algorithms in order to simulate those devices, right? So you have these problem specific methods that work in certain regime of certain types of devices, and then you have general purpose methods, right? So in photonics community, we are typically working with general purpose methods. So that's generally how people go ahead and do simulations. But there are, of course, certain classes of devices that are interesting in photonics, like metasurface and so on, which are somewhat harder to simulate with these general purpose methods. And then you might want to look for a problem specific method there.
What is the situation to use the fast multiple method?
So fast multiple method, actually, I probably shouldn't have put it there. The fast multiple method is rather a numeric algorithm that allows you to, that can be applied in many, many different EM methods. So for example, if you take integral equation methods, right? So in integral equation method, you end up setting an integral equation matrix, and you need to invert that matrix, right? Solve AX equal to B with an integral equation matrix. The fast multiple method gives you a efficient way of doing the inversion of that matrix, right? So fast multiple method can be put together with integral equation method. It can be put together with transfer matrix methods and a couple of other methods that fit into that format. So it's more of a mathematical technique as opposed to a numerical method. So I think I made a slight mistake. I shouldn't have put it there. But in a physics community, when people say fast multiple method, in electromagnetics, they're typically referring to a transfer matrix-like approach for 3D devices. Right? And you can apply transfer matrix-like approach to 3D devices if you can think of your device as a collection of scatterers, right? So if you can embed it in some homogeneous medium. So if you have a device that looks like that, for example, meta surfaces are very well approximated with devices like this. So they're essentially, meta atoms that are embedded in a simple background medium, and then you can use these fast multiple methods to simulate these meta surface devices pretty accurately. But if you're looking at some integrated optical devices, they're typically more complicated, and you can't really apply these fast multiple methods there, right? Does that make sense?
Yeah.
Okay, excellent. Great. Yeah, so I'm happy to talk about these other methods, which I probably know a little more about than finite difference time domain after the lecture if you're interested, but we'll focus on simpler things today. So we'll do FDTD. So I'll give you an question. No. Okay, so I'll give you an overview of how we can set up an FT. So what are the basic mathematical steps? So, you discretize, yes, but there are some subtleties that go into implementing FDTD. So just a very brief overview. I'll do it with a 1D example, right? Because it's easier to understand. And then I think what we'll spend more time on, we'll have a break after this first part. And what we'll spend more time on is basically trying to see how we can use FDTD to analyze, cavities and photonic crystals and waveguides and so on, right? Okay, great. So let's start with FDTD. Okay, so well, this is the first thing to keep in mind really is what is FDTD doing? So solving Maxwell's equations, and I probably don't need to remind you all of Maxwell's equations, but what you essentially have is you have these two curl equations. You're solving it in time domain. So your electric field and magnetic field are functions of position and time. So what do you feed into the simulator? So you feed in your device. So your device is a permittivity distribution and a permeability distribution. Of course, an optics permeability is almost always 1, but there is no restriction. You can feed in a permeability distribution if you're trying to model, let's say, a magnetic device. And then you also need to tell how you're exciting your device. So that's typically through a current source chain, right? So you put in a current source that creates some fields. And so the input to your simulator are going to be permittivities and current. And what it is going to give you is an electric and magnetic field as an output. So this is the black box of FDTD, right? So it takes in information about your device and excitation, gives you the field as an output, right? So, and in the second part of this lecture, we'll talk about how you can extract useful information from the field, because, if you want to plot band structure, the field is not the band structure. So you need to do more post-processing on this field to be able to extract the band structure. So we'll talk about that later, but that is something that you have to program or use on top of FDTD. So with FDTD, this is the basic functionality that you get access to. Okay, so what you essentially want to do is solve these time domain equations. So you have your electric field as a function of position time, magnetic field as a function of position and time. You have two partial differential equations that you need to solve. Right. Now, of course, electric field is specified at all points in space and at all times, right? But when we are doing things on a computer, we can't really go and specify we can't store continuous field data, right? So if you have an actual problem, where you need to specify, can you guys see my cursor? Is that visible? Yeah. So you have an actual problem where you want to specify where your fields are specified at all points in space. Right, and everywhere in space. And you want to convert this into what is a computational approximation of this problem, something that you can store in memory, right? And so there you essentially have to do two things. Well, obviously you need to discretize. So you need to sample your fields at some finite on a lattice of sorts, right? And typically we use this squared lattice, and we'll talk a little bit more about this lattice in a minute. And you also need to truncate your simulation, right? So you need to put some kind of a boundary on the simulation that tells you what region you're looking at. You can't simulate an infinite space, so you need to truncate your simulation. So there are two things that you have to keep in mind. So you need to have a strategy for truncating. How do I make a box around my simulation and go about solving Maxwell's equations in it? And I want to calculate electric field at specific positions and time. Okay, so with this in mind, let's try and set up a simple 1D example. So, well, in 1D, what you have really is that your permittivity and your permeability are functions of position, right? So they are functions of x. You just have one axis x. And you have Maxwell's equations that reduce to this simple form. Because it's 1D, you can assume, let's say, your electric field is polarized along the y-axis, and your magnetic field is polarized along the z-axis. So they're going to be, both perpendicular to the x-axis, and x-axis is the axis along which they vary. So in 1D, you just reduce to a simple scalar problem, right? And so these are the two simple differential equations that we get that we need to use for 1D Maxwell's equations, right? So we need to solve this. So now let's begin to discretize. So when we discretize this, we need to sample our electric and magnetic field at finite number of points. Now, there are many ways in which you can go about doing this sampling, right? And if you look at finite element method, they essentially allow you to choose how you want to go ahead and discretize your Maxwell's equations. But in finite difference time domain method, what is typically used is a electric and magnetic field are discretized on staggered grids, right? So what I mean by that is actually depicted in this figure. And so what you have here are that you have these blue dots telling you where the E grid is. And you have these orange dot telling you where the H grid is. So you're sampling your electric field on, let's say, a grid, right, on X. So let's just think about X for the time being and forget about T. So you want to discretize of both position and time, but let's just think about X. So if you have E as a function of X, right, then you can sample it at n points along X axis, right? And for magnetic field, we sample it at points that lie at the center of the segments of the E grid, right? So I'm going to sample my magnetic field at points which are here, right? So which are displaced by half a unit cell with respect to the E grid. Okay, and in time I do the same. So I'm going to sample my electric field at at a bunch of time instants which are governed by some time discretization delta t. And magnetic field, I will sample at time instants that are displaced along the time axis by a delta t by 2. So again, I'm staggering my E grid in both time and position. And although I've shown this to you for 1D, the same holds for 3D. So in a 3D problem, you can still go ahead and do the sampling. So your electric field is sampled on a, let's say, a cuboidal grid. In 3D, your magnetic field is going to be sampled on a grid that is displaced by half in each direction. But in 3D, you need to sample all the different components. So it becomes a slightly more complicated sampling scheme. So it's called the EE lattice. If you're interested, you can look it up. I won't show you the full-blown 3D thing, but the idea is the same. So now why do we stagger it is a question, right? So why do we stagger the E and H grid? And the answer to that is that we want to make you get an approximation for the derivatives that is accurate, right? So when I want to discretize these equations, I want to write this derivative as a difference, right? So I'm differentiating electric field with respect to space, or I'm differentiating electric field with respect to time. I want to be able to write this differentiation as a difference because in my computational approximation to this problem, I only know electric field at a finite, at a list of positions in space. I don't know it everywhere. So I need to be able to replace this derivative with a difference. Okay, and so you can do that in many different ways. What we typically want to use is what is called a actually I don't remember. There was center to end difference. So the point is that if you want to write the derivative of electric field at any point in space, then the 2 points that you're going to take the difference of should be on either side of the point at which you're calculating the derivative, right? So, and that gives you the most accurate derivative information, right? So if you want to differentiate electric field at one point in space, you could have calculated the difference with respect to a point that lies in front of that point in space, and you could subtract the electric field at the point that you want to calculate the derivative. So that'll be a forward difference because you're taking a point which is in front and the point at which you want to calculate the derivative. That'll give you a somewhat inaccurate estimate for the derivative, right? Because the point at which you're calculating the derivative doesn't lie in the middle of the 2 points that you're taking difference of. Or you could do a backward derivative, or you could do a center derivative where you take 1 point to the left, 1 point to the right, and you take a difference to get the electric field, the derivative at the center. And it's intuitive that this is going to be accurate, but you can actually mathematically see this with Taylor theorem for electric field as well. But those are details. I don't want to go into that much. So now how does this help us? So let's take one Maxwell's equation. So let's take the derivative of electric field with respect to time. So this is just a rearrangement of the Maxwell's equation that I showed you here, which is the second one. So you have derivative of electric field with respect to time. You can write it in terms of the derivative of magnetic field with respect to space and J, right? So you can do this. It's pretty simple. And now let's try and impose this equation at a particular point in space and time. So where do I, so let's, let us impose this equation at this point, so which I made drawn inside this box, right? So this black point here. So now let's see, if you're differentiating the electric field in time and you want to evaluate this derivative here, you would, to get an accurate approximation of the derivative, I'll take 1 point on top and 1 point on bottom, right? So I go 1 step up and 1 step down and write this as a difference of these two electric field at the same time. So the lower index here is the time, the upper index is space, okay? So I go 1 point, the upper index is time, lower index is space. So at the same position in space, because I'm differentiating with respect to time, I calculate the difference between the electric field at 1 on top and 1 on bottom, right? And when I'm differentiating the magnetic field with respect to space, then I go horizontally because now I want to keep the time fixed and calculate the difference, right? So now I keep the time fixed. So I go at these 2 points and take the difference. So I get this difference here. And then this J, you need to sample exactly at the center. So the J needs to be sampled at the black dot. And the permittivity also needs to be sampled at the black dot. So if you think about this a bit, the way we translated this differential equation into this difference equation, so you immediately see why I needed to stagger the grid, right? The reason I needed to stagger my E and H grid is because the derivative of E with respect to time is equal to the derivative of H with respect to space. So if I'm taking center differences, I need my electric field and magnetic field to be staggered in both space and time, so that when I take a derivative with respect to time in E and a derivative with respect to H in X, I end up evaluating them at the same point. Does this make sense? Right? Are there any questions? I'll pause for a few minutes here because this can be slightly confusing when you look at it first. So if there are any questions, we can go over this again. But once you understand it, it's actually really simple to even imagine the 3D case. Okay, any questions?
When you say that you have to stagger it to make sure they line up in the same place in time and space, the same point on the lattice, is that like a hard requirement, or is that more just to improve the accuracy?
It's to improve the accuracy. You don't need to do that. You can always use, so this is so that I'm using the center approximation for the derivative, right? So if I'm calculating derivative, I want to go at a point, I want to go to the left and right and take a difference, as opposed to taking a difference with a point only on the right or only on the left. So a derivative with a center difference gives you an O of delta square approximation, whereas a derivative with a forward or backward difference gives you an O of delta x approximation, right? So it's one order less accurate in terms of delta x. I mean, it could still work. So maybe if your simulation is, if you reduce your delta x to be small enough, it might still work, right? But you can, with this center approximation, you can get away with larger delta x's. And still do accurate. And this is actually, if you look at literature on FDTD, people also look at higher order approximation for the derivative, where instead of just approximating the derivative with 1 point to the left and 1 point to the right, they approximate it with many points to the left and many points to the right? So these higher order derivative allow you to essentially, so if you think about the Taylor series expansion, so your Taylor series expansion of a function is f of x naught plus the first derivative term plus a second derivative plus a third derivative and so on. This center difference approximation essentially allows you to get rid of error coming from the second derivative term, right? Because when you go to the left and right, the contribution of the second derivative is the same because it depends on delta x squared. So when you subtract it, it cancels, but you still have error because of the third derivative term and the fifth derivative term and so on, right? So, but if you use more points on the left and right, you can keep on getting rid of higher derivatives in it, and you can get increasingly accurate, more and more accurate versions of finite difference time domains. So they are called higher order implementations. But then the issue then it becomes is then you need the number of points that you need to compute this derivative goes on increasing. So one of the advantages of FDTD is that it's a very sparse method. So if you want to update electric field at a particular point, you only need to look at the fields in its neighborhood. And that actually allows a very efficient parallelization of this method. So because you can implement this on GPUs or multiple CPU cores and divide up your simulation and distribute it. But if you start using derivative information that requires a lot of data, then that parallelization starts becoming more complicated. So there is a trade-off there. So it's an accuracy versus speed trade-off, but higher order derivatives have been used. These higher order FDTD methods have been used in harder problems with varying amounts of success in the computational EM community. Any other questions?
I have a question. Sorry.
Oh.
Yeah, sorry.
You can go.
Yeah.
So I have a question on the source. We're given a source. Is this source the induced source from the permittivity distribution?
No, this is a free source. The permittivity distribution is captured at this epsilon of x term. So this source is the source that, so imagine, so okay, maybe the more intuitive thing to do is to think about an incident field that is scattering off a device, right? Maybe that's more intuitive, right? So you have some kind of a plane wave or a waveguide mode that's scattering off. So the way to think about this source is if you were to remove this, so if you were to remove this permittivity distribution that you're simulating, so if you were to remove the device, what current source would you use to set up that incident field? Okay. So if you just had that incident field, then what current source would you use to put it in?
But in the case, for example, of simulation of metals, maybe that's what you are asking about. You would have a J term, which is taking the same place in FDTD, but there would be an extra equation that describes like Lorentz or Drude model. And then J would basically describe permittivity, frequency-dependent permittivity.
So that's more complicated.
It would be exactly at the same place in these equations that Raul is describing, but here this is just a driving force, right?
Right. So this is not the, so this as written here, this source is not the source that the permittivity that the polarization currents inside the permittivity distribution are inducing. Okay, so this is the source that's exciting the incident field itself.
It's just like an antenna, right? And there are a lot of different subtle things that you can do with that. You know, you can do kind of like harmonic source if you know exactly what you would like to excite and with certain spatial distribution. I mean, if you do like Dirac impulse in time, then that excites all the frequencies, and then you can do filtering. There are kind of filtering methods in FDTD. And since it's time domain method, then you cannot really do frequency filtering, then you have to do convolution in time domain. So there are a lot of, you know, subtle things that you can do afterwards, but in, you know, typically what people do is, you know, you excite some frequency range where you know your resonance is, and, you know, you put these antennas or dipole sources where you know your field would be excited. Yeah, and actually in connection to our class, you can actually use the same model to also look at the light matter interaction. I mean, you can just put a dipole, classical dipole, and look power radiated, and the ratio between power radiated by this kind of dipole when you have some structure and when you have no structure would be also Purcell enhancement. I mean, you can do it from that classical model, and that's what you already have in FDTD, commercial FDTD these days, yeah. I don't want to interrupt, I just...
Yeah, no, thank you. Does that answer your question?
Yeah.
There's another question, I think.
Yeah, how do you deal with the boundary?
Yeah, I'm coming to that in a minute. So good question. Okay. Yeah. So yeah, I will come to that in a minute. So as correctly noted, so this actually works if I'm working at a black dot which is in the center, but suppose I hit a black dot here, or like for example this black dot, one which is on the edge, and then when I try to do a finite difference of maybe the magnetic field, that I don't really know what to put on the right. So we'll come to that in a minute. So the boundary is somewhat tricky to handle, right? Okay. And you can do the same process with the other field, right? So your other equation, which relates a time derivative of magnetic field to the space derivative of the electric field, and then you would impose it at a complementary position. So if you remember the first equation we imposed on this black dot, which was lying between two orange dots and two blue dots, and that's because we wanted to access the time derivative of electric field. So it needed to be vertically in the middle of two blue dots, and we wanted to access the space derivative of magnetic field. So it was in the middle of, horizontally in the middle of two orange dots. But now we want to do the other way around. We want to access the time derivative of magnetic field and the space derivative of the electric field. So we have to go to this grid as opposed to this point, right? And then it's exactly the same. So the time derivative of magnetic field, again, I will look at the same time, and I'll have to use two same position, and I'll have to use two orange dots. And for the time derivative, space derivative of the electric field, I'll use the same horizontal axis and use two blue dots and write down my update equation very similarly. Okay, so this is how you can discretize your equations at the center, and I hope you guys are appreciating why you need the staggered grid, right? That's kind of the point of this exercise, to make that explicit. And now let's go to the question of how you deal with the boundary. Well, so now, for example, if you try and discretize this equation at a dot that's lying on the boundary, then you can write the time derivative of the magnetic field just fine, because you have two orange dots, one on top and one on bottom. But when you start writing the space derivative of the electric field, then you can write a space derivative on the left, but you don't really have a space derivative on the right, right? So you don't have an electric field point on the right. So here is where you have to start thinking about what boundary conditions does your problem that holds for your problem, right? So any simulation, any solution of a partial differential equation is incomplete without the specification of a boundary condition, right? So now, depending upon what you're simulating, you'll start using different boundary conditions, right? So there are a few boundary conditions that we can talk about. So maybe the simplest boundary condition to understand is that you have a perfect electrical conductor, right? So you just put a PEC conductor on the boundary of your simulation. And when you put a PEC conductor on the boundary of your simulation, then you just can set the electric field here as 0. Right, because you have a PEC there, so the electric field is going to be 0. So that solves the issue of writing this finite difference on the boundary, right? Or for example, if you are dealing with a periodic structure, right? If you're dealing with a periodic structure, then you have periodic boundary conditions, right? So if you're dealing with a periodic structure, then the boundary condition, then the electric field at this point is just equal to the electric field at the beginning of your simulation, right? If the length of your simulation is 1 period. So you can just replace the electric field here with the electric field here, and you can still write down your update equation, right? And for periodic structure, often you want to understand how your periodic structure is behaving with respect to a source that is exciting a block mode. So instead of imposing a periodic boundary condition, you want to impose a block boundary condition, right? And the block boundary condition, as you know, is that the electric field at the beginning and the end of the period are not equal, but they're related by a phase that depends on what your block vector is, right? So your electric field at the beginning and end will have an exponential I phi. Well, there is no problem imposing block boundary condition with the FDTD simulation again, because you just need to write the electric field here as the block phase multiplied by the electric field at the beginning of your simulation. And the same thing holds for the magnetic field. Does this answer your question?
Yes.
Okay, great. So now you might ask, like, what about the boundaries in time? Well, that's a moot question because you will just simulate up to the time you need your electric field, right? So you can go on simulating up to time t, and you can always write these difference equations to relate field and time t to fields at previous time. So you don't really need a hard boundary condition in time, but in space you need a boundary condition, right? Now, of course, these boundary conditions that I've described are special boundary conditions. In practical problem, you don't really have a PEC boundary conditions. There are use cases of block boundary conditions. If you're trying to simulate band structures, and you would use block boundary conditions. But most often you're trying to simulate problems in which your fields are just radiating away, right? So they are radiating away. They're not really meeting a perfect electrical conductor or a periodic interface, but they just radiate away in free space or in your device, right? 10, 20 years back, people did a lot of research on how to handle this radiation boundary condition. So there were a lot of absorbing boundary conditions that people came up with that worked fine to some extent. And for structures which confine light pretty well, like cavities, so in which the amount of radiation is not very large, you can actually get away with using absorbing boundary conditions. So they are fine to use. But if you are looking at structures at which there is massive amount of radiation, for example, if you want to simulate a device whose sole purpose is to scatter light, so then using absorbing boundary condition was not that great of an idea. And there was a seminal paper in computational E&M community that introduced what's called a perfectly matched layer. And this is what is used. This is state of the art in almost all the commercial software, as well as open source FDTD software that you can find in the current research community. It all uses perfectly matched layer. So perfectly matched layer are somewhat harder to describe. So I'm not going to go over the details, but just to give you an intuition, what perfectly matched layer they basically do is that if you want to simulate radiation going away from your device and not really reflecting, you can imagine one very intuitive thing to do is put some kind of an absorbing material around your simulation region, right? And if that absorbing material is 100% absorber, so it absorbs every light that's incident on it, then that's great, because that absorbing material can essentially mimic the behavior of infinite free space, right? And absorbing materials, what they would do is they would exponentially damp the field inside the material. So if you put an absorbing material, then you would exponentially, the fields inside the absorbing material will exponentially decay. So at some point they'll become actually quite small, and then you can then put some other boundary condition like a radiation boundary condition, or you can even just put a perfect electrical boundary condition because your field would have gone to zero because of an exponential decay in your problem. Okay, so now the trick that the perfectly matched layer paper solved was to have an absorbing material that would not reflect, right? So if you imagine putting an absorbing material at an in front of vacuum or in front of a bulk medium, then that because of the absorption of the material, there would be reflection as well. It's not going to perfectly absorb. But what the PML people do, they figured out how to calculate a permittivity, an absorption coefficient, or a complex permittivity distribution for the absorbing material, so that the reflection is zero for almost all incident angles, right? So it isn't zero at every incident angle, but you can make it zero at a pretty large range of incident angles. So they were able to mimic an almost perfect absorber, and that allowed them to terminate their simulations very, very nicely. Okay, so that's what's used in today's day and age. Now, so we are going to take a slight break here before we go into how you can simulate devices, but maybe I can ask a simple question so then you guys can try and answer. So one question that I often think, one question that I had when I was studying these computational E&M things is that, okay, well, you want to simulate, these scattered fields, and you want to make your fields go to zero. You want to put some boundary condition on your field, right? And so, but if I put a PEC boundary condition that is sufficiently far away from my device, right? In 3D, we know that the fields would decay as 1 by r, or 1 by r squared as you go for, or 1 by r, sorry, as you go further and further away from your device, right? So if I just put a PEC boundary condition at a sufficiently large distance, will that work? So that's a question, right? So do you see the question? So remember, the way we were terminating our simulation, if you were to put a PEC boundary condition, is to say that the electric field here is zero, right? The electric field there is zero, so you can then write down your finite difference equations properly, right? So if you go to a sufficiently large simulation size, electric field is nearly zero. So if I just impose PEC boundary condition on a sufficiently large simulation volume, does that give me accurate result? And the answer is no, it doesn't. No matter how large simulation you make, it will not give you completely accurate result. But perhaps someone can offer an explanation to that. Does anyone have an answer? So why can't you terminate?
It doesn't. Oh.
Yeah. Go on,
it doesn't conserve energy.
Doesn't conserve energy. You're on the right track, but maybe refine it a bit.
Maybe a hint, can you, since this is optical microcavities class, can you simulate, can you simulate resonators if you put perfect conductor actually at infinite distance and you have your resonator at the center? Can you capture two factors?
So yeah, so the way to think about this is that, the PEC bound, one way of thinking about this is the PEC boundary condition is a perfect mirror, right? That's intuitively what we understand. So now what, if you imagine you have your device is radiating some power that's hitting this perfect mirror and it's going to reflect all of this power, right? And one way of thinking about how, so all of the power that your device radiates is going to be reflected by a PEC mirror, no matter how far it is. If there is no absorption, no matter how far it is going to get reflected and it's going to interact with your device again, right? So you're going to get an inaccurate simulation because even though your fields are very small at the PEC mirror, when they're reflected, they're going to come back and create significant fields on your device, right? And one way of thinking about why this does not contradict the fact your fields are vanishing as 1 by r is that your pointing vector is vanishing as 1 by r squared as you go away from your device, but the area of the PEC mirror is also going as r squared. Right? So the entire pointing vector is interacting with this huge PEC mirror and all of it is getting reflected back into your device. So that 1 by r, you need to do something better than that 1 by r squared dependence, right? To put a PEC. So if you were able to make your fields fall off as 1 by r cubed, for example, then you would be fine because your PEC mirror is just growing as R squared. The reflection that it's going to give you is growing as R squared. So the integral of the pointing vector times area, which is the amount of power that's actually being reflected, is growing as the area is growing as R squared. Your pointing vector is scaling as R cubed, and you're fine. If you go sufficiently far away, you'll get an accurate simulation. And that's one of the reasons why you can put a PML, which exponentially damps your field, and put a PEC boundary condition after that. Because once you have an exponential damping, that is much stronger than a polynomial increase in the size of your boundary, right? So then you have a guarantee that, you know, if you make your simulation large enough, well, how large, of course, depends on what simulation you're actually exactly doing. But if you make your simulation large enough, you're going to get accurate results. Okay, does this make sense? Right? Okay, cool. So we'll take 5 minutes break and then finish the rest of the slides. I think we just have 5, 6, 7 more slides.
Yeah, I just wanted to make a brief comment since we're on the break right now, and Raul already touched upon that, is the time of the simulation, because this is a time domain method. I mean, how long do you decide, how do you decide how long do you need to run your simulation, you know, to obtain your result? And of course, this is a time domain method. So frequency resolution is inversely proportional to the duration of your time, of your simulation in time, right? So if you want to have very fine resolution in frequency, if you're simulating high Q resonator, or you are actually capturing something that has a very small line width, right? Or some sharp changes in the line width, then your simulation needs to be very long, right? Because the timing, the frequency resolution is inversely proportional to the duration of the time. And of course, there are other conditions for convergence, which relate the stepping in time to the stepping in space. I mean, there is a fundamental kind of convergence criterion for all FDTD methods, but this is just related, since Raul mentioned boundary in time, right? Which is kind of duration of your simulation in time. So there is no boundary in time, but when you stop depends on how fine resolution you want to have.
Yeah, we'll talk about that in a minute as well, on cavity simulations. Yeah.
For the example you just mentioned, can you truncate in time before it reaches the very far PEC boundary?
You could, if that's your interest, yes.
Okay.
Yeah, so if you take a very far away PEC boundary, you'll see that till the fields start interacting with your PEC boundary, you'll actually have accurate simulation, right?
Yeah, but you know, keep in mind that you need to load all of this into your basically computer memory, right? So
so it's impractical for sure.
Yeah, you're getting into a hypothetical scenario where your boundary has to be so far that you cannot really simulate that on any computer, right?
Yeah.
Yeah.
So in theory, what you're saying works fine, right? So if if for example you have a waveguide based device, you want to calculate transmission inside the waveguide, and you want to ignore the fields that are radiating away, not into the waveguide mode, and you send in a pulse which is narrow in time, and you can keep track of when does the pulse just come out of the waveguide, but it is not really interacting with the boundaries, and you can at that point, you know, take your data, calculate, analyze the transmission. But it's very hard in practice to be able to do that. So if you try and do this in practice, you'll go crazy because you have to keep track of exactly when you're stopping simulation, and you need a pretty large simulation domain. So it's also, you just use a PML. So PMLs essentially solved all of these problems for the field, so no one really thinks about it anymore. So you just put PMLs, you truncate it. With PMLs, you can in fact truncate it at pretty small simulation sizes. So you basically just need in practice half a wavelength around the device that you want to simulate. You don't even need, you know, to put many wavelengths. So just half a wavelength, and you put PMLs, and your simulations are pretty accurate, almost at that level.
Yeah.
Of course, that you need to fine tune that for specific problems, but they work pretty well. But yeah, as I mentioned, sorry.
Yeah, no, go ahead. Sorry.
Yeah, so as I was saying, for certain problems, you can use absorbing boundary condition. Like for cavities, absorbing boundary conditions are good because they are trapping a lot of light and very little of it is radiating away. But if you're using waveguide-based devices or free space scatterers, absorbing boundary conditions are not as great of boundary conditions, and PMLs are pretty much what people use. Yeah. Yeah.
Yeah, I mean, perfect conductor is not the best choice, right? For and pretty much most of the problems.
Oh yeah, no, none of them.
I mean,
Yeah.
so what people used to use, what Raul said, absorbing boundary conditions basically means that you are kind of discretizing the equation for outgoing plane wave at the boundary, right? You know, if your wave looks like a plane wave at the boundary, then you just write the equation in finite difference time domain for outgoing plane wave and discretize that equation, right? So it's like a different
Right.
that governs behavior. But you know, of course, then even if you're simulating a resonator, is what you were asking, you have to be sufficiently far. You can't slam that right next in the near field because it's not going to work, right? You're not, your wave is not outgoing plane wave. And you know, of course, that you just need like 2 layers to simulate that. And for PML, you need much thicker layer. So the, you know, there was a trade-off even like after PML papers were published on what consumes less RAM, you know, when you're running simulation. But now with modern computers, it's not of an issue, right? Because you can actually pretty much simulate PML always.
Is there any guideline to put your how far to put the PML boundary?
Well, I mean, yeah, it kind of depends on your problem. In practice, I've found that if you just put it like one free space wavelength is fine. Like if you just put like a one wavelength box around your device and then you start your PML. And in practice, I think, well, 10 cells of PMLs typically work fine for most of the simulations at optical wavelengths and telecom wavelengths. Of course, you might want to vary that to see, you might want to like increase that slightly to see if that increasing that is changing your simulation numbers drastically, and then you know that you need larger ones. But in practice, I feel that one wavelength box gives you the right result. Yeah, but that's just a very rough guideline. There's no hard and fast rule there. Yeah, and one thing about PMLs, I mean, we can discuss PMLs more if people are interested, but one thing about PMLs is that, so PMLs are not perfectly absorbing for very oblique angles of incidence, right? So what basically governs how far you put your PMLs is that you want to make sure that the PMLs can absorb all angles of incidence that are incident on it. And then you run into same trade-off as with absorbing boundary conditions. So with PMLs, you don't need it to be a perfect plane wave or a spherical wave. But if you have evanescent waves that are interacting with PMLs, they'll actually radiate through. Right, so even with PMLs, you kind of have to be far enough so the evanescent waves in the device have decayed, and all that you're hitting it with are plane waves that are not very oblique, right? So if you're simulating a device that has very strong evanescent field, you might have to put your PMLs somewhat farther away from the device. So it does depend on the physics of the device you're working at. For most optical waveguide-based simulations, for most optical devices, one wavelength to two wavelengths works well in practice. Okay, does that make sense? Yeah. So I don't want to go into too much in details of PMLs as setup. So there's like a computational ENM class that's offered, which goes into these details. And so if you're interested, you might want to take that class as well. Cool. Any other questions? No. Okay. So let's go to the second part. As I was saying, modeling nanophotonic devices. So the first part was just to tell you, what are the different, how an FDTD roughly works. So you have a boundary condition, you have discretization in both space and time. And then there are some considerations, as Yelena was saying, there's a stability consideration, there's an accuracy consideration. So we'll come to that in a minute in context. And then those considerations are somewhat heavily dependent on what exact device you're simulating with. And I think it's generally a good practice to make sure your numerical simulations are converging. It's not a very well followed practice in my experience, especially in photonics. I note that a lot of people put simulations that are not convergent to paper, which is not the best idea, but it's a good practice to see if your simulations change drastically, if you reduce your step sizes or if you add extra regions of space between your PMLs and your device. So all of those things should be tested out, right? But you shouldn't go crazy about it. You don't need accuracies in your efficiencies that are like 1 E-6 relative or converge to X arbitrarily small amount. But that's one thing that you have to keep in mind. And we'll come to that at the end of this slide. So, but I think what's more important is that what you really want to calculate is not really the electric and magnetic field for the device. I mean, in practice, what you want to calculate is the device metric, right? So as we talked about, we have these simulators here. So we pass in permittivity, permeability distribution, and source. We have an FDTD simulator, which of course also takes, what boundary conditions I am imposing. So PMLs and then mesh size delta X and delta T. So it needs these pieces of information to be able to simulate these equations. And then it gives you these electric and magnetic field as a function of position and time, right? So within the simulation domain at the points that you have tried to simulate it at, right? But you're not really interested in this electric and magnetic field of position as a function of space and time. What you're interested in most cases is to extract some useful metric from these simulations, right? So you want to extract something that says something about your device. So if you have a resonator, you want to extract quality factor and electric field mode. If you have a photonic crystal, you want to extract a band structure as an example, or if you have a waveguide, you want to extract the band structure of the waveguide. So one thing to think about is how we go ahead and do these post-processing. Now, if you're rich, if you have numerical with you, it does most of the post-processing for you most of the times, but it's still a good idea to understand how it's going about doing it. And if you're not rich and you need to use open source software like me, then you sometimes have to program these post-processing yourself. And having an understanding of how this post-processing happens is useful so that you don't go crazy programming these post-processing all the time. So now let's start with simple example, which is highly relevant to this class. It's on nanophotonic cavities, which Ellen has already mentioned to some extent. So I'll go over this very quickly. So if you want to simulate, let's say, the quality factor and the electric field mode of a nanophotonic cavity, then how do you go about doing it? So, well, what you imagine is that, well, let's say if my cavity is a high Q cavity, right? If you've designed it well, it's a high Q cavity, and this method would work even for some low Q cavities. What you do is you excite the cavity with some energy, and you try and then see as time goes, what is the electric field what the electric field looks like, and that gives you an estimate of the mode. And you can also look at the spectrum of your electric field to get an estimate of what the resonance frequency and the quality factor of the cavity look like. So in practice, what you would do is if you want to simulate a cavity, and this is how actually numerical also does it, in your cavity region, you can put a dipole source, right? So you put a dipole source, so it's a source in position in space, but we often in practice, we would either put like a delta function dipole source, so which would excite all frequencies, or you can also put like a dipole source with some spectrum around the resonant frequency. If you have an estimate of where the resonant frequency is, you essentially put a dipole source, which is a Gaussian in time, and the temporal width of the dipole source can be decided by what delta omega you want to probe your simulations over, right? And then this temporal width is also going to inform what the discretization is going to be, right? So if you can't really simulate a dipole source which is narrower than the delta T of your simulation. So you have to keep in mind that the time width of the dipole source that you're putting in should at least be maybe an order of magnitude or 2 order of magnitude larger than the delta T that you're using, right? Oftentimes I've had people show up results where they are nothing, my simulations are giving me 0. That's because their source is smaller than your delta T of your simulation. Obviously you're going to get a 0. So you have to be careful about one of these things, right? So what delta T, what is the width of the dipole source that you need to use? Well, that is governed ultimately by the quality factor of your cavity, right? So if your cavity is very high Q, then you need to sample a very narrow line width and frequency, and therefore you would need a pretty broad pulse to be able to get a narrow line width. So which is good news because you can take a somewhat broader pulse and then still be able to sample the line width. But if you have a very, very low Q, so you are very broad in frequency, then you would need a very narrow pulse so that you excite all the frequencies that lie within the line width of your cavity, right? So that tells you how you will choose the delta T of your dipole source. Then, so in order to get an estimate of the quality factor of the cavity, what you could do is that you can measure the electric field or magnetic field. It doesn't really matter because both of them are going to oscillate at the frequency of the cavity and decay with the quality factor of the cavity. So you can choose to take, let's say, electric field and magnetic field at some point inside the cavity where it's non-zero. So you would like to not, so another point about where you want to put this dipole source and where you're measuring. So you shouldn't put them at symmetry forbidden points. So based on the symmetry of your photonic crystal, often there are points where your field is 0. right? So if you put your dipole source as a point where your electric field is 0, you're going to get 0 field. Your dipole source is not going to excite your cavity, and you're going to get nonsensical result. So it's always good to put some random dipoles, so which are not at a symmetry forbidden point, so that you're confident that you're exciting the cavity mode. And then you can look at the electric field as a function of time and watch it decay, right? So if your simulation happens, so you can now end your simulation at a time where the decay is almost complete, and that will be, of course, governed by the quality factor of your cavity. And then you can Fourier transform that resulting electric field to get an estimate of what the line width of your cavity looks like, right? So that's roughly what you would do. Sometimes you have very high Q cavity. So if you have a very high Q cavity, you might have to simulate for days on end in order for your electric field to decay to 0. So often, but if you have a high Q cavity, that also often means that that your electric field has a very nice exponential decay, right? If you have a high Q cavity, your decay is pretty much a very nice exponential decay. So you can often fit a decaying exponential to the electric field as a function of time data without really allowing that decay to go to 0. So you can truncate your simulation before the decay stops and fit an exponential and still get very accurate estimate for what your quality factor looks like. And there is a package that has been developed by Stephen Johnson in MIT, which is called the harmonic inversion package. I don't know how many of you have heard of it. It is not something that Lumerical uses, but it's a very recommended tool. So it's based on what's called in signal processing a filter diagonalization method. So the problem that it basically solves is that it takes a signal in time and it fits a bunch of exponentials with an oscillating exponentials on that signal as a function of time. And it doesn't need you to wait for that signal to decay completely. So you can take like a signal that is not decayed completely. So you prematurely end your FDTD simulation, and still you can get pretty accurate estimates of this quality factor and frequency. So this is what the filter diagonalization or harmonic inversion method does for you. So if you're simulating pretty high Q cavities, I would recommend not simulating for very long, but rather investing compute in your post-processing. So you truncate your simulation a bit prematurely, and then you use this filter diagonalization method to get very accurate estimates of your line widths and resonant frequencies. Okay, so this is cavity. So it's somewhat of a simpler problem to simulate. So let's think about another problem, which is photonic crystals. And this is something that many of you asked a question about. How do I go ahead and calculate the band structure of photonic crystal? So let's imagine I have a 2D photonic crystal, and I want to calculate the band structure. So I want to produce a plot that looks something like this, right? So in order to calculate the band structure at a particular K, what I really want to do is take a particular K and calculate the frequencies that can exist inside the photonic crystal at that particular K value, right? What does a given K tell me? It tells me what are the boundary conditions that my block mode needs to satisfy, right? So to simulate this photonic crystal, all that you really do is that you repeat the same exercise that you did with a cavity. So you take one unit cell of the photonic crystal. You don't need to simulate the entire thing. You just take one unit cell of the photonic crystal, and you use block boundary conditions to terminate the simulations on the unit cell, right? Because if you're simulating at a particular K, you know what the block boundary conditions are going to look like. And then you put a source inside this block boundary, inside your period, and you again do the same thing as a cavity, and you excite your source with a bunch of frequencies. So you can use a delta function source to sample all the frequencies, or you could use like a Gaussian source if you're interested in band structure in a particular range of frequencies. So when you simulate, when you're excited with this delta function source, and you look at the electric field inside your photonic crystal at any point, right, which is not a symmetry protected point, and you look at the Fourier transform of the electric field, again, what you're going to see are peaks at the frequencies at which you have a block mode, right? So for example, this is essentially what it would look like. So this is a 2D example. That's why you get a very clean spectrum. If you have a 3D example, you get a more noisy spectrum. So in a 2D example, you can put like a simulation boundary here, and I impose block boundary conditions. So the field here is exponential I phi 1 given by kx of your block vector. Field here is exponential I phi 2 given by ky of the block vector relative to the field at the beginning of the period. And you put a dipole, you simulate the entire spectra. And when you calculate the electric field as a function of, when you do a Fourier transform of the electric field, what you're going to see are these very sharp peaks at the resonant frequencies corresponding to your block mode, right? And this is going to tell you where your omegas are. So this one simulation allows you to calculate a vertical slice of this band structure plot. And then you can vary these kx and ky to get the entire band structure plot. Okay, does this make sense? Okay, cool. So,
Yeah. So the math you talked about earlier for the FDTD simulation, it was all real fields. But when you introduce this phase, you introduce like an imaginary component. So
well, you can do Fourier transform with of an imaginary field, right?
Okay, but it actually solves only for the real fields, right?
No,
So
no. If you're imposing block boundary condition, your fields are complex, right? Because you think of your update equation. You have an exponential I phi in your update equation.
Yeah, but where does that play into the equations for the fields as a function of time and space? I guess those are also imaginary.
Yeah. The E as a function of position and T becomes an imaginary field. So you just take Maxwell's equations and your electric field and magnetic field are both complex as a function of position in T. It's artificial, right? Because block boundary conditions are not really a real problem. In a real physical simulation, you will only have radiation boundary conditions, and then you have real fields. So this block boundary condition is artificial. So we are trying to impose a boundary condition to probe the band structure. So that is why you're getting this complex field, right? So you see what I'm saying, right? So the complex field is not a contradiction here. And the place why you need to be complex is because when you impose your boundary condition on this cell, you introduce a complex number exponential I phi in your simulation. So you end up getting complex update equations. So even if you start with real fields, they'll become complex at some point. And you can do this Fourier transform business on complex fields, right? And again, even for these simulations, you can use harmonic inversion package. So you can fit a bunch of, well, in this case, just sinusoids and not really decaying exponential on your signal. So you don't need to simulate for an indefinitely long period of time. Okay, does this make sense? Any questions here? Yeah, and one point that I would like to make here, and actually we'll briefly talk about that in the next slide, but any questions? I don't have too much time, so I'm rushing a little bit, but any questions?
Do we, so for band structure, you need to do multiple simulation, each with different
case, yeah, exactly, yeah.
But these are small simulations, you can start them in parallel, right?
Yeah, exactly. So just one period, right? And in typical photonic crystals, it's like maybe half a wavelength by half a wavelength or smaller. That would be a period. So it's very, very fast simulation. Okay. Okay, cool. So let me take a last example, and that's of a waveguide. Right, and I mean, this is exactly the same thing as a photonic crystal. It's just a 1D photonic crystal, right? There's periodicity in one direction. So now you want to probe a band structure that looks something like this. Let's see if I do have a spectrum for this. So yeah, I want to probe a band structure that looks something like this. So now it's a function of only kx because you have one propagation direction. So now what you do is, again, to simulate this band structure, you do the same thing. You take up one period, which is now going to be one unit cell in the x direction, but along the other direction, it is going to be an infinitely long simulation in principle, but you can terminate it with some kind of perfectly matched layer in one direction. So you impose PMLs in this direction, and you impose block boundary condition in the other direction, right? And you do the same exercise. So you put a bunch of dipoles, you excite them with as delta functions or as some Gaussian, and then you look at the electric field going as a function of time. Again, it's going to be a complex field because you have a block boundary condition, and you look at the Fourier transform of the field, right? So you have this sharp peak appearing, but you also have these sidebands that are not as sharp. Right, so there are some broad sidebands, right? So can someone tell me what these are? What are the broad sidebands versus the sharp peak? So I'll give you a hint. If you look at a perfect 2D photonic crystal, which is 2D as in, which is a 2D simulation, and you simulate and you do the exercise that I just mentioned, you will only get sharp peaks. You will never get any broad spectrum. Okay. But if you do but the moment you start terminating with PMLs in one direction, you're just going to start seeing this broad spectrum. If you take the 2D photonic crystals that Yalan has been talking about, in which you have a slab, so you have a 3D simulation, then you have to impose block boundary conditions in two directions and PMLs in the third direction, then again, you'll start seeing these broad spectrum.
Is that a guided wave?
The broad spectrum is the guided wave?
Yeah.
No, the broad spectrum is radiation mode. The sharp spectrum is the guided wave, right? The guided mode is essentially the block mode that you're looking for, right? So the guided mode is what sits at a particular frequency. So if you take a K, right? If you take 1K, then the guided mode has a very well-defined frequency at that K, right? So when you're imposing block boundary condition, you're sampling this band structure at K. So you get a very, very well-defined peak corresponding to your guided mode, right? But you also have radiation mode that form a continuum. So all of these radiation modes, they exist at many, many, many frequencies at the same K, right? So corresponding to these radiation modes, your emission happens in a broadband fashion, right? So this, and you can actually simulate the band structure of the photonic crystal that has been used to make this waveguide. So if you just take the photonic crystal on the left and right, you'll find that this region is the band gap, right? So you have a guided mode that lies within the band gap of your photonic crystal. Outside the band gap, you're radiating into the photonic crystal. So you have radiation modes that are basically the photonic crystal modes that are carrying your power away. So you get like a more broadband response of your dipole over there, right? So this allows you to separate out, so the Q factors of the peak allows you to separate out what the radiation modes are and what the guided modes are. So one question that you could ask is then, well, how do I decide which is a radiation mode and which is a guided mode? Can anyone answer that question? What would govern the Q factor of a guided mode peak versus a Q factor of the radiation mode peak? So in principle, should a guided mode have a Q factor at all? Let's say you had a perfect simulation. If you're solving Maxwell's equations exactly, would the guided mode have a Q factor at all? It wouldn't, right? Because it's at a very well-defined frequency. If you impose block boundary condition, the guided mode hits one particular frequency, right? So the broadening that you see is a numerical artifact. So the broadening that you see is a consequence of you terminating your simulation at a particular time, and because of your discretization. So with this, if you try and increase the time of your simulations, right, then this peak is going to become narrower and narrower, right? So that, yeah.
Yeah, go ahead. Yeah, no, finish. And I just wanted to add something. Yeah.
Yeah. So if you, so the discretization in frequency space is inverse of the time of simulation, right? So how long your time signal is. So if you make your time signal sufficiently long, so if you take your simulation to be sufficiently long, then the guided mode peaks are going to become narrow, whereas where the radiation mode peaks are going to stay as thick they are because their Q factor is a physical thing, right? So it's the Q factor of the radiation mode peak is not limited by your simulation. So that is one way of figuring out which one is a guided mode peak, which one is radiation mode peak. But in practice, what you should do is you should always have an estimate of the band gap of the surrounding photonic crystal. So if you have an estimate of the band gap of the photonic crystal that you're making your waveguide with, then you know where you're going to see these radiation modes and where you're going to see the guided mode. And in the 2D slab case, you would have an estimate of the light cone, and then you could have an estimate of where you're going to see radiation modes and where you're going to see guided modes. Okay, yeah, Yelena.
I just wanted to add a brief comment about these blue shaded regions. That's not something we talked in the class. And typically, if you're interested in photonic crystal waveguides, the first thing that you do before you simulate a waveguide, you simulate the whole photonic crystal. So here it would be square lattice photonic crystal. And then what is shaded in blue here is basically the whole band diagram of the square lattice photonic projected onto this gamma x direction, where is the waveguide direction. So the first step is you find the blue region, which is projection of the whole band diagram from for unperturbed photonic crystal onto this diagram. And then when you simulate photonic crystal waveguide mode, which is for one direction, then you exactly know that these peaks that Raul was explaining are falling inside of the blue region, right? So you know that where the yellow region is, and everything in yellow region would be your waveguide mode. Okay. And I don't.
Okay, yeah, great. So that's about the end. So I gave you a couple of examples and we're out of time. So sorry about taking more time here. And these are just some tips that I consider important for students who are doing simulation. So you want convergence. So I'll not go over these, but please get your simulations to convergence. That's very important. So I'll upload them and you can read them in greater detail if you like. And I just wanted to say that if you're more interested in computational E&M and maybe trying to program some of these simulations yourself and understanding the lower level details and how these simulations work. You don't need it if you're trying to just use them for designing devices, but if your research is more on the computational theoretical side, then you would typically benefit from being familiar with these tools, because a lot of techniques that we use in computational E&M, they can be imported to other physics simulation in like quantum mechanics or acoustics and so on. So, generally getting an idea of how these things work is good if you're interested in doing theory or computation research. So there is a course, EE340, that's sometimes offered. I don't know, it is being offered rather erratically the last few years, but if you get an opportunity to do that class, it's a good idea. And there are some books that I personally like quite a lot. So, and where I took a lot of the results in this slides with, and I've linked, it'll be on the slides that you can go and see. Okay, so I'll upload these slides, and that's all I had. Great. Okay, thank you.
Thank you all. Bye. See you
Okay,
around.
bye.
And I should also say that we'll try to also enter grades within the next couple of days. So we're working on that, and I'll send an email when that happens. I mean, of course, this is a pass-fail quarter, and I have no doubt everybody's doing well, but just so you know, it's going to happen within the next few days. Okay. Thank you all, and I'll see you around. Thank you.
Thank you.
Bye.
Thank you so much.
Thank you.